Welcome and thank you for watching our webinar. Before we start, I'd like to point out that we are on a mission to raise money to develop a cutting-edge well-time module for our open source community. Our success for this project hinges on your involvement. You can make your contribution by visiting our website, www.dgbes.com. There you'll find a direct link to our GoFundMe page. Every donation, big or small, brings us a step closer to our goal. Also, I'm excited to announce that we have an exclusive offer as we approach the end of the year. Any purchase made before the year concludes will be rewarded with an extra month of OpendTect Pro, absolutely free. It's our way of saying thanks for your continued support. Enjoy the webinar.
Welcome to this webinar on the OpendTect Attribute Engine. The Attribute Engine is one of the defining features in OpendTect, and what we will do in this webinar is discuss what the Attribute Engine is all about. We'll discuss a few of the principles behind it. We look at free versus commercial attributes. Then we dive into the attribute definition window. We show you where you can find help on attributes, and we discuss the layout and various features of the Attribute Engine window. The focus of this webinar is on chained attributes. That is, attributes from attributes, and in OpendTect you can really use this to do quite stunning things with seismic and combining horizon and seismic data, doing all kind of interesting features. I'll wrap it up with a demo on how to do certain things. So let's start with the attributes in OpendTect, the principles. We use the definition of Turi Tanner. What is a seismic attribute? Basically, seismic attributes are all of the measured, computed, or implied quantities obtained from the seismic data. And under this definition, if I apply a filter to the seismic data, then that filter is also an attribute. If I transform the data, the transformation is also defined as an attribute and can be found in the Attribute Engine. We have something that we call meta attributes in OpendTect. These are attributes that are created by combining multiple attributes in an intelligent way to do something specifically for what the user wants it to do. Typical example is the seismic chimney cube, where we combine tens of different attributes through a neural network to classify seismic data into seismic chimneys or non-seismic chimneys. Then we talk about chained attributes, and chained attributes are defined as attributes from attributes. Now, attributes in OpendTect are like recipes describing how to compute something. The actual computation is done either on the fly, and you can apply an attribute on any active display element, whether it's an inline, a crossline, a random line, a C-slice, a small volume, or along a horizon. It's all done on the fly. Or you can apply and compute an attribute in batch mode, and if you have set up your system for distributed computing, then you can use all the computing power that is available to you to compute these attributes. We support pre- and post-stack attributes, but you have to define these in what we call an attribute set before you can use them. And this you have to do for 2D seismic and for 3D seismic separately. An attribute set can be built completely from scratch, or you can start from a whole range of default sets and then use these as is, or start editing and create your own proprietary set from these default sets. Now, what are free attributes in OpendTect? Most of the industry standard attributes in OpendTect are supported as free open source attributes. Included are several quite interesting ones, some of them unique, some of them very valuable. If you use these in other software systems, then you will have to pay dearly for these. Examples are spectral decomposition, and in OpendTect we support various decomposition methods like short window Fourier transforms, continuous wavelet transforms, empirical mode decompositions, and more, because in Wayne-Mock's attributes you will also find a number of spectral decomposition methods. Trace matching is an interesting one, where you can align seismic datasets. That is very handy for 4D seismic datasets, but you can also use it to align near, mid, and far stacks. Fingerprint is a unique feature where you can tell the system, like, this particular location, for instance, I found in a well oil or gas at this location. I would like to know where else is the seismic attribute response similar to the locations that I have identified as being interesting. So what you do is you create a number of attributes, and then you combine these into a fingerprint that matches the data to that fingerprint. So if you apply it, you get a value back from 0 to 1. 1 means it's exactly the same as the fingerprint at the locations where I've created the fingerprint. Pre-stack attributes are supported, like AVO attributes and various derivatives. We can compute angle stacks in the data, and then we have the set of attributes from Wayne-Mock, which are nowadays shipped with the software. Very interesting attributes in that set. Among others, AVO attributes, spectral decomposition attributes, an attribute to compute and apply mistie analysis to seismic, to align 2D lines in a 2D seismic grid. And my personal favorite is the external attribute, which allows you to write your own attribute in Python and use it directly into OpendTect. Now we come to the commercial attributes, and I'll start with dip steering. So dip steering, what you can do with the dip steering plugin is you can compute from the seismic how the seismic reflectors are dipping. So you get new volume with dip information. And from this dip steering cube, you can calculate several attributes which are quite interesting, like the polar dip, the azimuth, the volume curvature attributes. But what dip steering also allows you to do is to compute multi-trace attributes in a better way by computing the response along the seismic reflectors. And this you do by dip steering. For example, if you look at a free attribute similarity, then in the free version it will be calculated like this. This is the evaluation position, and you just horizontally extract the information to compare these seismic traces on how similar they are. Now, if the seismic is dipping, then you are comparing apples and pears. But in the steering mode, what you do is you go from the evaluation point, you follow the dip outwards to find the dip at this position, then you follow the dip outwards to this position. So basically you are constructing a virtual horizon from the evaluation point. And then you extract the information along this virtual horizon, and that gives you dip steered similarity. And we can do that with any multi-trace attribute in the system. So we also do it for filtering the data, and that kind of filtering is called structurally oriented filtering. And I will come back to that in my demo when I demo the dip steered median filter and I talk about diffusion filtering. More commercial attributes, if you have a horizon cube license, then you will have additional attributes in the attribute engine, like you can compute horizon cube density, which clearly shows you where you have unconformities and condensed sections. If you have FracTex plugin by Geo5, then you can compute seismic anisotropy from texture attributes. If you have the deterministic and stochastic inversion plugins from Earthworks and ArcGIS, then you will find this entire implementation under the attribute engine, under the EW set of attributes. Also colored inversion, spectral bluing, frequency shaping, and post-decode, which are all plugins by ArcGIS that change the amplitude frequency spectra, can be found in the attribute engine. Also, some of our faults and fractures plugin attributes are found under the Attribute Engine, amongst others the fracture density and fracture proximity. But if you are looking for the thin fault likelihood or the fault likelihood, one of the main attributes from faults and fractures, you will not find it in the Attribute Engine. You really have to start up the faults and fractures control center. Similarly, for the edge preserving smoothing filter, it's only in the faults and fractures plugin and not in the Attribute Engine. Second note, we also support a number of filters from the volume builder. A free plugin in this context is the recursive Gaussian smoothing filter, which is an extremely fast smoothing filter, and also a plugin developed by STMage, MGS destriping for footprint removal, is found in the volume builder and not in the Attribute Engine. And now let's continue and have a look at the attribute definition window. First of all, if you are stuck or you want to know more about a certain attribute, then press this icon here, the question mark. It will immediately bring you to the relevant page in the user documentation. So this is context sensitive help. Next to it is another icon, which is launching the attributes table. And the attributes table is giving you all kinds of attributes that you can apply for a particular geological problem that you're trying to solve. For instance, you're looking for oil and gas, you will find a whole list of attributes that can be used for that kind of application. And then you can, pressing the link in that table, search further and you get to the right attribute with more information on what this attribute does, how it is computed, where it will work, where it will not work, with references to literature and so on. Okay, now this is the attribute definition window, and we will go through a number of other features of interest. And let me start with that one. This one starts the default set, so you can import a default set into your current project. The system will ask you what is the seismic that you want to apply these features on, and if you are using a steering cube, so if these are dip steered attributes, then it will also ask you for a steering cube. And after this simple specification, you will have the whole list of attributes in your own project to work on. This is an important icon because it allows you to do movie style parameters. Every attribute has one or more parameters, and these parameters can be evaluated either by changing the parameter and reapplying the attribute to your display element, or you can do it like this, where you say I'm going to calculate a whole range of different parameters with different parameter settings, and then I can movie style select the one that I find best. I'll demo this later in my demo. You can build very complex attribute sets, so like a complete processing scheme to where you want to actually get your data, and if you do that, you may get a little bit confused by all the connections on where is my input, where is my output, and where is the actual data flowing from one attribute into the next. And for this you can use this icon over here, which visualizes the data flow. It requires that you install the GraphViz Flow software, which is a free plugin. Now, more parts of the user interface. If you define an attribute, then this will be added from here. You give it a name and you add it, and it's added to this list. So this is the attribute set that you will eventually use and can save in your system. The attributes are grouped in different groups, like you have attribute groups for the frequency attributes, the statistics attributes, different types of groups, so that you can find these attributes back if you're looking for a certain attributes. There's also one with all, and then you get all of the attributes available, which is a huge list of different calculations that you can do. Each of these attributes, like this one is the volume statistics, will have some input parameters like what is my input, what is the different things that I can change, and what is the output. And this block here defines whether you want to apply dip steering or not. And that is only available if you have the dip steering plugin, if you have a license for that. Next, we have this icon next to the definition. So you add your attribute to your set, and then if you press this icon, you will apply this attribute to the current display element. And if you press this icon next to it, you will launch the batch processing module, so you can distribute it over the entire network, all the computers that you have access to, or you can just run it on your own computer. Now let's look at chained attributes. Chained attributes, basically any attribute can be computed from a data that is on disk, or it can be computed from an attribute that you have defined before. So that is, the input is then an attribute and the output is another attribute. In this way you can build complex chains, and you can construct these to process and manipulate data in various ways. And especially useful in this context are of course the mathematics attribute, which returns a mathematical expression. You define it yourself. You can include logical functions like if then else, and you can use or start from rock physics equation, because this is linked to our rock physics library as well. Other interesting attributes in this context are the reference attribute, which returns position information like X, Y, Z or inline crossline value. The reference shift, which shifts the location where I'm actually going to calculate the attribute response. The horizon attribute, which allows me to combine horizon data with seismic information, because what this horizon does, it returns information from a horizon. That can be the Z value, or it can be some horizon data saved with the horizon. It returns this and puts it everywhere along the same seismic trace. So then I know at every sample position what the horizon information is belonging to that trace location. Volume statistics is an important one because it computes statistical properties like minimum, maximum, median, standard deviations from a small volume or from a small disk, and the disk can be dip steered, so from something in your data. And then we have the position attribute, which computes an attribute at a position where another attribute has its maximum, minimum or median response. An example is a diffusion filter where we evaluate the quality of the seismic based on the similarity, and where the similarity is highest, we then borrow that amplitude and move it into the position where the quality is less. This is the way we do it in a diffusion filter, for instance. Now that brings me to the demo, so let's look how it is done in reality. Okay, let's now look at some real attributes. I'm popping up my 3D attribute definition window, where I've already prepared a couple of attributes, as you can see here. And if I want to know more about, for instance, this one, the bulk shift, which I have given this name bulk shift here, but it is actually a reference shift, which is part of the positions group. And then I can get more information about this attribute by clicking on the question mark, which brings me to the user doc where I can find more information. And another way of getting more information about attributes is by clicking here in the attributes table. The attribute table gives me a number of things, geological things I might be interested in. For instance, I'm interested in fault detection. Then it gives me a number of attributes that I could try out. And here, for instance, similarity brings me to this table where I can find more information, describes what it is doing, multi-trace attribute. And it also gives me references, and this brings me back to the user doc. So there's more information on how to use these things. Now, I'm going to start with this one here, dip-steered median filter via the volume statistics. So the dip-steered median filter, we actually have it also as an attribute in this list of attributes. So if I go and not look at one of the groups, but I look at all of the attributes, then I get a huge list here. One of these attributes is actually the dip-steered median filter, and I can compute a dip-steered median filter myself. But let me just show you what this user interface looks like. Dip-steered median filter, I input the original noisy data, I specify the radius, and I also specify that I want to have it steered using this steering cube, so it's tracking along this horizon. And I can output the filter or the residual, and I call this dip-steered median filter from the SM attribute, and I add this as a new attribute to my list. You see here a third icon, which I haven't explained, but in many of these help windows we also have made videos on the topic, and if you press this one it will bring you to the video that is about dip-steered median filtering. Now, instead of showing you how to play with this dip-steered median filter, I'm going to actually play with this one, which is exactly the same, but now this is the way it is actually calculated using the volume statistics attribute. So in volume statistics I specify the input, and then I specify how much of the seismic I want to extract around the evaluation point. In this case I specify a time gate of 0 to 0 in a step out of 2 in both directions, so I'm getting a radius, and I'm doing this dip-steered so that it is actually following the seismic reflector, and I'm outputting of all the amplitudes that I'm collecting in this way the median value, and that is my output. Now if I apply this, then I need to apply it to a particular element, so I'm adding an attribute layer here, and now I can either put in something from store data here or some steering cube information, or I can apply one of my defined attributes. So I'm going to apply the DSM via the volume statistics attribute, and it's now calculating the dip-steered median filtered response on this one. And that should be cleaner. It should have removed a lot of the noise. And indeed, that's what it did. So that is good. Now, instead of playing around now with these parameters, because I can change the radius to see which radius would be the best case for this dip-steered median filter, I'm going to evaluate this parameter using this icon over here, movie style parameter. There are two parameters that I can play with in the volume statistics. There's the time gate and there's the step out. Now the time gate I want to have 0, 0 because I want to follow the horizon, and I don't want to mix up amplitudes from above and below. I'm going to extract initially a step out of 0, 0. That means I'm getting a return of the original seismic data. I'm going to increase the step out with 1 by 1 in both directions, and let us do this 5 times. And now we're calculating the dip-steered median filter with a step out of 0, 0, which is the original one, then of 1, 1, then of 2, 2, then of 3, 3, 4, 4. And once these are all calculated, I can movie style inspect the one that I like best. So that is why I'm not doing this on the entire line. I've just shrank the area of investigation to just this small area so that it's going faster. So here I can now use my slider to see what the effect is of the increase of this parameter. And as you see, the larger my step out, the smoother my data becomes. Now in this case, I probably would like to be between 1 and 2. And that depends a little bit on my personal taste. If I would accept 1, 1, then it would accept this and my user interface is updated. And now we come to chaining of attributes. I would like to see how much of the information has actually been removed. So I'm going to define a mathematics attribute, and in the mathematics function I'm saying let's subtract the original seismic data from my dipstier median filter result. I can use my own parameters. I can use x0, x1. Variable names are completely up to the user themselves. But once you press this set button, you will have to specify what do you want to use for original. In this case, that's the original seismic. What do you want to use for DSM? I want to use DSM via the volume statistics. So that is the attribute that needs to be calculated first. And that will be the actual residual noise. Now I'm going to replace this information, which is currently the dipstier median filtered result, by the calculation that I'm going to do now. So it's calculating the dipstier median filtered response, and then it's subtracting this one from the original data, and that is the noise that I have removed from the data. That is pretty incoherent, so I'm satisfied that this is indeed a good filter. Okay, I've not mentioned this rock physics button here, but this rock physics button is allowing me to use all kind of rock physics calculations, which I can just copy from here into my my formula, and I can then start using that from here. So we have quite a number of density calculations, and basically you can copy even this complex function into that that mathematics equation here, and then start filling it in. Also, this mathematics function, this is this very simple one we just subtract. We have logical functions, we have mathematical functions, statistical functions, constants, and we have some other information. So constants are like pi and Euler E, and the undefined value. So this is also something you can use if you don't know how to do certain things. You can just say, okay, I want to use an undefined value in my equation. Then you look for it here and you insert it. And then you see that that is actually undef. That's how you, or this would be the Euler E value. Similarly, with logical functions, you can see these are the type of things you can use in an equation, and for math you can use these type of things. If you want to use a square root, then you insert it like this, and you know how to do it. Okay, and again, of course, you can press here the question mark if you don't know what to do. Okay, let's remove this this one, and let's move on to something else. Let's have a look at another section. For example, we have this seismic prediction, and that has been predicted inside a time gate. Let me do it differently. I'm going back to this later, because what I want to do first is just let's look at a simple bulk shift. Yeah, so if I want to bulk shift my data, then I can do that through the reference shift. I'm going to make this my active element. In this case, I've defined my bulk shift as shifting the dipstier median filter cube, which is the one that we see over here, by 50 milliseconds. And if I do that, and I'm pressing this button now here, so I'm applying it to the current version, then that looks like this. And in the same color scheme, it would look like this, so I can compare that indeed it has been shifted 50 milliseconds. Now that's an easy way of shifting your data. Now let's look at something more complex. I have this prediction, and that prediction is actually only valid between these two horizons, the green and the yellow horizon. But it has computed between these two intervals. Now I want to cut off the top and the base part. How do I do this? I'm using the horizon attribute. And the horizon attribute asks for a seismic cube, and then it also asks for the seismic, so the horizon that I want to use, and that is in this case the FS4 horizon. And I can output either some horizon data, or I can output the C value in seconds, and that's the one I'm outputting here. So let's look at how that looks. I will put that in here, and I'm going to do it like this: attributes CFS4. So this means, again in the same color scheme as we are going to compare the porosity later on, this means that this value at the CFS4 horizon is now available all along my seismic line. It's the same value everywhere, and I can use that value in my calculations. I'm doing the same for the CFS8, and that is the value for the CFS8 horizon. Now to compute the porosity only, or to only leave this value within the interval of interest and blank out everything else, I'm using undefined values, and I'm going to define this formula. If this actual C value is larger than the C value of the FS8 horizon, and the C value is smaller than the one from CFS4, then I will output something, and otherwise I will just put an undefined value there. And undefined values, they can be made transparent in the color bar that I'm using. So then when I press this set button, it will ask for what do you want to use for the CFS8. It recognized that C is something that I can use as real C. C FS8, that's my horizon attribute that I've defined here, and I'm using for the CFS4 formula variable also that horizon that I've defined up here. And I output the actual porosity volume that I have calculated and shown in the previous slide. And that will be the porosity that is only available between these two horizons. So I'm going to press this, and now we are overlaying this one, but now as you can see I have blanked indeed the one above and below. So these type of manipulations, they're possible with using the right combination of horizon data, references, reference shifts, positions attribute, but especially also the mathematics formula that you can use to do really fancy stuff in OpendTect. Now, the last thing I want to show, and this is just for those who really want to go further than what I have shown here, is let's have a look at another attribute in this set. This is a default attribute set, and there is something that we call a fault enhancement filter. There's a fault enhancement filter which has been compressed so that you only have to filter to fill in the parameters that you need. But there's also a fault enhancement filter for the expert, which really gives you all the attribute steps that you are going through with the mathematical expressions to get to the final result. It asks me for what do I want to use for the seismic and what do I want for the steering, so the dip steering volume. And now I've imported my attribute set, and what we see here is that we have a dip steered median filter, that is this one with a small step. Small step is 1 by 1, and then we have a dip-steered filter with a larger step, 2 by 2. We have a similarity calculation, which is based on the dip-steered median filter with a small step. It's dip-steered, and then we have what we call a dip-steered diffusion filter, and that is based on this position attribute. So what we do is we calculate the similarity within a certain radius, and that is fully steered, and if that similarity is maximum, then at that position we will calculate the dip-steered median filter with a small step. So the dip-steered median filter from a position where we have the best quality seismic is now transformed into the evaluation points where we will actually want to use it, and that is what is called a diffusion filter. Now, what is a fault enhancement filter then? That is basically a combination of dip-steered median filtering and diffusion filter, where again we are using the quality of the data based on the similarity. In this case, we evaluate the quality. If the quality is good, we would like to apply the dip-steered median filter. If the quality is bad, as we can expect in the vicinity of faults, we want to use a diffusion filter so that we can borrow good quality seismic into the bad zones, into the fault zones. And we do that along the dip, so it's dip-steered, and then we have our faults enhancement filter. Now, in this equation, note that we are using C0, so we have constants like C0, C1 that we can actually fill and use in our equations, and these constants will also be recognized as a value that once I've pressed set, I can actually give the parameter value. So I could have specified 0.5 here, but I can also do C0, and then it will say give me the value here. The advantage of that is that otherwise I would have to specify for each time I'm pressing set all the different inputs that I need to do this calculation. And moreover, if I want to do a parameter evaluation, I can evaluate on C0. So I can evaluate on the cutoff in this equation. So the cutoff says if the similarity is larger than this cutoff, apply the median filter. Otherwise, apply the dip-steered diffusion filter. Now, that is more for the ones who really want to dive into it. Look at the default sets. There's a lot of stuff there where you can learn how to do certain things. And with that, I would like to stop this webinar, and I'm opening the floor for questions. Thank you very much.